All right, moving right along, I would like to introduce our next speaker, Dr. Peter Cundall. Dr. Cundall did his doctoral work at the Imperial College in London, and there he developed the distinct element method for modeling jointed rock and granular material. His career has included 5 years as a consultant at Dames & Moore, 7 years as faculty at the University of Minnesota, where he is currently an adjunct professor, and more than 20 years at the Itasca Consulting Group, headquartered here in Minneapolis. He is the author of numerous and widely used numerical codes, among them FLAC, FLAC 3D, UDEC, PFC, and several others. His paper, A Discrete Numerical Model for Granular Assemblies, is the most cited paper in Geotechnique. He is a fellow of the Royal Academy of Engineering and a member of the National Academy of Engineering. Please join me in welcoming Dr. Peter Cundall.
Yikes. Didn't realize how bright it was. Anyway, now for something completely different. My background is that I retired 11 years ago, and I was on this nice, gentle ramp towards obscurity when Joe Labors yanked me out of my, sleepy slumber, and here I am. Thank you very much, Joe. That's actually sarcastic. So. I'm going to talk about the art of numerical modeling. You may think numerical modeling is sort of based on numbers and formulas. So where does the art come? It's widely used in geomechanics for design, diagnostic purposes. But it's not just a question of plugging in the data and hitting run. We need to understand the underlying physics and whether the model properly represents it. And the art really consists in convincing yourselves and others that you're doing a good job of representing what's actually going on. The notes in this paper come from many years, probably 15, 20 years of helping users with Itasca codes. These are the following codes. And just for those of you who are not familiar with these codes, hang on, didn't mean to do that. For those of you not familiar with these codes, UDEC and 3DEC simulate systems of angular blocks, like jointed rock. FLAC is a continuum model with nonlinear stress strain laws. PFC is a particle flow code which models spheres and disks. And XSite is a lattice code. All these codes are coupled with fluid flow. I should say that I was the original author of all these codes, and they've been developed since then. But in a sense, they're like my children. So I've had this sort of father's outlook of the people abusing codes are similar to people abusing children. And I don't like it, but I've seen it quite often. So in my view, the most important thing in modeling is understanding the mechanisms. You have to convince yourself that what is actually happening in the system, especially if it's very nonlinear and it's very complicated. But if the model's too complicated, the mechanism may be obscured. Thus, I would suggest that simple models should be constructed. Obviously, we've got to do the complicated model for design purposes, but I think simple models should be constructed. And two examples of this are presented as follows. Here is something quite complicated, which is an arch dam, and it's usually set in a very complex topological scenario with many faults and joints. There's lots of things you can do with this model, but this particular objective is to determine the valley displacements that arise from water impoundment. So we add water to behind the dam and find out what happens to the displacements of the valley. And this is actually quite important in a project we're working on, where people are, I mean, these are very high dams. This is a 300-meter high dam, so that the displacements can be quite large. So we make a very simple model, just a U-shaped valley. I know it sounds very simple, but it gives you some insight. So there are two time scales. First of all, in the short term, when we add the load, within a matter of seconds, basically, the rock deforms and you get these horizontal displacements, vertical displacements. It's actually inwards. And this is what I call, I've coined the term a mattress effect, because if you push down on a mattress, you find that the displacements go down and they go inwards. And in fact, I did the experiment on the couch at home. I had to do it single-handed because my wife was out of the room for a short period, and I think she would have been upset. But anyway, I definitely confirmed that the mattress effect works. The other is a long-term effect. When the fluid migrates into the surrounding rock, you get a bulb of pressure here that actually counteracts that load of the fluid. So the net effect is upwards and outwards. So the resulting displacement field is a combination of both competing effects, mattress and swelling. And then when we come to do a full-scale analysis, we can look at the displacements and say, does this conform to our intuition? We've actually gained some knowledge. We actually did a big run at the beginning. We couldn't understand the results. So these simple models give you some insight into what's happening. The other second example of a simple model is in hydraulic fracturing. We want to study how fractures interact. So here we have two simple injection points. We use this code XSite, which models brittle rock by lattice of springs. And I'll show you a picture of this. So these springs are elastic. And when you apply loads to this, some of these springs can break. And this corresponds to a microfracture. Whenever a spring breaks, we put in a fluid node. So if there's fluid as a boundary condition, this can go in here. And of course, you see it's fully interactive in the sense that if fluid gets up to here, that acts as a fracture tip, which can then cause more cracking and so on. So that's this lattice code. These are side views of a three-dimensional simulation. There are clouds of microcracks which correspond to these breaks of these springs. The green one was the first one, and then we inject the second from the second cluster, and we note that when they're close together, the second set of fractures kind of curves inwards towards the first one, but when the the spacing is far, it goes the other way. It actually repels. So it'd be interesting to know why this happens. So I made a very simple model with a flat axisymmetric continuum. So this is the axis of symmetry. We put a slot here and a slot here and just pressurize them. And noted the angle of the major principal stress from the horizontal. Now, typically fractures will propagate along the direction of major principal stress. So if you imagine there's a major principal stress coming from here, and if we plot the direction of this up or down in degrees versus the spacing, you see there's a 0 point. So if they're at a certain distance, then principal stress is horizontal, so the cracks will tend to go horizontally. But for a smaller distance, they tend to converge. So this really is an explanation of what we see in that more complicated model. Things like diagnostics are very important. However complicated your model is, you may have everything in there and faults, joints, the whole works, but they're all simplifications in reality. So probe the limitations by making changes and let the model tell you what's wrong. So going back to that example, you notice the boundaries are pretty close for that fluid migration. So if we extend the boundary, so we get this change in displacement. So clearly the boundaries, we can deduce two things from this. First of all, the artificial boundary is important, and we should be careful where we put them. And secondly, what is the actual condition in the field? Is there a fault at some distance that acts to prevent the fluid migrating, or is there a fault that conducts fluid? So we can ask the people in the field to do some more measurements. I'll talk about a few of these misconceptions. So I'm going to go through some of these. I'm not going to go through all of them because otherwise I'd be out of time. Boundary conditions, it may seem stupidly simple, but they're actually quite important. I went to a lecture several years ago by a really famous professor. If I mentioned his name, you know who it was. But I'm not going to do that. And he showed a simulation of a slope, stability with plasticity, and there was active plastic flow at the artificial boundary. So, it's invalid. So I did raise my hand and said, what's your problem, mate? In many cases, you can get a lot of understanding from a 2D simulation of a 3D problem, but sometimes it's invalid. If we have a footing and we look at the displacement under the footing load, you might think, well, let's do a 2D plane strain model. But actually, with plane strain, there's no depth at which it converges. It just goes on forever. That's for a uniform thickness, whereas for a 3D or axisymmetric, obviously we get a convergence. This is a bit unrealistic because in reality there'll be a sort of gradation of properties, so naturally it'll get stiffer as you go deeper. So, but it's just to show that you can't automatically assume a 2D model may be good for everything. This is the thing that gets up my nose quite a lot. It's time dependence, because it's so widely misunderstood. I was on a big project with all these mining engineers. I mean, they were really good people, and what they do is on big open pit mine slopes, they measure continuing displacement. So they have these monitoring devices which show a change of displacement with time. And then said, well, you can model it with plastic flow. Well, no, you can't, because plastic flow in regular plasticity theory has no time dependence in the usual formulation. It flows and then it stops. So it's a bit, and they didn't understand this, and these were pretty experienced engineers. So there are many mechanisms that could account for this. For example, some kind of time-dependent property of the material itself or the joints. This one's a big one, change of fluid or thermal conditions. Progressive fracturing, you have subcritical crack growth in many situations. Particularly in open pit mines, you have weathering and erosion that changes the stiffness and stress state. And sometimes people actually overlook that there is construction going on, which accounts for it. So This is a book that was written about 10 years ago by this whole consortium that I was talking about. These are all lots and lots of people, and it's a big fat book printed on glossy paper. So it was quite a big undertaking. But there is no entry for time dependence. This is, totally amazing to me. I complained to them, and they said, not important. And there's no mechanism for time dependence in the mechanical models. They do talk about fluid flow, but they don't talk about what the effect of fluid flow would have on the mechanical response. So, which is very strange, because in this book, they actually have plots of movement with time. They really stress the importance of measuring by extensometers and all these laser things, the movements with time in the rock, but they don't do anything about it. So this is weird to me. One big thing with time dependence is fluid interaction. So this is a common form. And what I think people should realize is that there are several time responses. In general, the response time is related to this storage coefficient, S. And there are a couple of forms of this. This would represent elastic storage, and this would represent the migration of the phreatic surface. And typically, the time scales are totally different. These are in minutes. These are can be days or weeks. So you should take this into account when you're making the model. You can, in fact, take advantage of it in modeling is you can use an algorithm that alternates between the fast one and the slow one. And you can make approximate physical approximations in each. In a simulation dominated by elastic storage, it's important to know that time scale, because first of all, it'll tell you where to put the boundary conditions. How far has that fluid gone in that particular time? So this is an important thing to consider. The next topic that people have some problems with is localization. Shear bands and tensile cracks are pretty common examples in geomechanics. And they have shear bands have a potential to occur in any model that embodies an elastoplastic material. Doesn't even have to be softening, but if we do have softening material, you should pay attention to how to minimize the dependence on element size. And there are lots of papers on this, and particularly in the code manuals and stuff. There was a good example on spontaneous localization by this Russian. He's quite an intelligent guy, and he did these studies on localization. He actually wrote his own code FLAC. So, he took the FLAC manual and coded his own code because he didn't want to pay for the license. So this is actually a FLAC-like code. So we see these shear bands for a particular value of friction, and also it's strongly affected by dilation. If you add dilation, it pushes the bands away because they interfere with each other. It's a shame because this guy was really good, but he went to the dark side. He went to Wall Street and now models, how to make money out of noise. Sometimes when you perform high-resolution simulation, even for a simple case, like a slope stability case, and I think Ethan Dawson is here, and he's probably going to be on a panel or something that talks about numerical modeling of slope stability. We model a slope in an elastoplastic continuum. This is perfect plasticity, but it's quite a high density of elements. And I've got something in here I'm going to use. Anyway, you get the expected slip surface. But on the toe of the slope, you get this weird set of shear bands. And they're actually that actually correspond to toppling. If you get a deck of cards, obviously you can't see this, but you can imagine it. If you have a deck of cards like this and you push at right angles, these cards are all doing this. They're doing this shuffling business, and that's really toppling at a toe. The thing is, will these occur in a real slope? Well, if we add dilation to the, keep the friction angle the same, but add dilation, then these things go away. We get the expected shear band. But this is an interesting exercise because it gives us something to look out for in a real slope. We might imagine a slope in a very fine-grained material which doesn't have much dilation, whereas it would be suppressed in a material with like a blocky rock structure. In fact, I showed this to somebody last week, and they got all excited, and they said, yeah, we've seen that in a slope, so apparently it exists. But normally, you imagine toppling, like if you talk to Dick Goodman, it occurs on the sort of crest of the slope, but this is occurring at the base of the slope. Then there's this perennial thing where people complain that they run the code twice and they get different results. Some physical systems are chaotic. A possible consequence is the behaviors. There are many aspects to chaos, including strange attractors and all the rest of it. But one consequence is the behavior is critically dependent on initial conditions. A proper numerical model will exhibit such dependence on trivial details. And this is not an error. We try to convince people this is not an error. This is what happens in reality. If you have a rock, for example, where you have cross joints like this, loading will cause it either to move to the left or to the right, depending on trivial details. In fact, we made a 3D model. My colleague Farron made a 3D model where he changed that crossing point very, very slightly and got two different results. And then in a more complicated model, you can have a very strong dependence on friction angle. So between here and here, the friction angle is changed by 1 degree on one of these joint sets. But it's still sliding on the joint sets, even with a higher friction angle. So you might say, oh, this is unrealistic for real rock mass because we don't have all these through-going joints. But somewhere, for example, if you make up a proper model with a DFN, discrete fracture network with staggered joints and all the rest of it, there will be some instances where you get chance occurrence of non-staggered intersections. And this will give rise to chaotic behavior in the sense that you make a very small change and it affects the results dramatically. And it can arise in many other systems, not just rock. This is the one I gave you an example for. So really, what you should do in this case is run many simulations with varying parameters and make a statistical analysis of those results. I'm always upset by when I see people present just one simulation because it's so complicated they can't afford to do many more. But it's just pointless. You should do many simulations with parameter variations. There are questions of instability as well. And you should be aware of the fact that this will occur. For example, that slope model we showed is an example of instability. It starts off by being elastic and it becomes plastic. With a code such as FLAC is a time-marching solution scheme, it should be able to represent the instability realistic and follow how things evolve. And once we know that it occurs, we know how to deal with it. So, but sometimes we can get surprises. This is a weird example. You may think this is a bit silly, but anyway. Here we have an elastic block resting on another elastic block. And we simply push this with a constant velocity. And we note that the friction of the interface is constant. There's no softening or anything. It's just constant, Coulomb friction. So we might imagine the results to be trivial, that uniform sliding would occur as soon as we exceed the strength limit. But this is, I hope this works. This is what happens when we run it with flak. These are velocity vectors. So it's just starting off now. It's a bit like a flag waving in the wind. But, so what the heck's going on? Well, in fact, these are slipstick waves. So as just by chance, it might be fluctuations in the normal force. If the normal force, be aware that this is very close to the static friction limit. Where the normal force is slightly higher, it will stick. When it's slightly lower, it'll slip. So that you get these regions, these black lines denote where it's slipping, and this is where it's stuck on the other lines. So these waves kind of self-reinforce, and you can see the reason for this is the normal stress fluctuates, and of course the shear stress fluctuates because it's proportional to the friction coefficient times the normal force locally. But there's a very interesting thing. This to me is fascinating. The mean shear force, is kind of a symmetry, doing this, but in fact is less than the static shear force for friction. So in fact, we find the thing can dissipate less energy than it should be doing. And if we vary the slip rate and plot that normalized shear force against slip rate, we get this slip weakening. So even though we have a perfectly constant frictional coefficient, we can get slip weakening taking place. The interesting thing is, will this occur in not only geological situations? I can imagine a sort of big overlying 50-kilometer slab, which is tectonic forces are pushing it, and it will suddenly go slip. Will it happen in that case? Will it happen in lab results? I mean, people have reported on slip rate weakening, and I've always been suspicious of this, but I mean, does that happen in lab tests? I actually tested this out. In my basement, I had a 2x4, and I had a little motor that went very slowly and pushed it. And in fact, it did. It had these little jumps. And it's not softening. The 2x4 had constant friction, as far as I can tell. So this is kind of an interesting effect. So in conclusion, we've stressed that it's crucial to understand mechanisms, and simple models can help in this process. But nowadays, you're getting more and more people are reporting on these artificial intelligence not simulations, but sort of black boxes where you use neural networks to kind of give you an answer. You give it lots of data, and then the answer pops out. I just wonder if this is a good thing, because it doesn't give you any understanding. It simply says, given this data, this is what happens. We examined some common problems and misconceptions and provided examples, and suggestions have made for good modeling practice. Expect the unexpected. Just like the instability problem we saw. I didn't expect that, but don't just say, oh, that's something anomalous, I better not report on that. Follow it through and find out what it's telling you. because often we can learn new things about the systems we're modeling, even though data is lacking. I mean, there used to be this saying, I can't remember what it was, but it was that you only get out what you put in. This is absolutely not true. A good model can actually give you more information and give you better ideas about some way that something's behaving. So there you go. Thank you.